it's increasing from negative infinity to 4.
Okay.
In other words, let me bring up my tablet here. Is that increasing or decreasing?
Hold on 1 second.
No, hold on, David. I screwed up her screen.
Okay.
Right here.
No, I don't know where you went.
Yeah, there you go. Okay, so that was, we're going to go back to this one here.
Just go to,
Actual size.
no, isn't that what you pressed before? I don't know. Go to this. And just go back to this. Yep. No.
Try it again. Hold on.
Go to 50. Okay.
That one better?
Okay, yep.
Okay, all right, Dave, we fixed it.
Okay, so you can see this red line I've drawn here? Is that
So that's it.
That's increasing, exactly.
Yep.
What's that?
That's decreasing.
And what is that?
It's both increasing and decreasing.
Okay, let me label some points here, and you tell me where it's increasing, where it's decreasing, and okay, so what interval is it increasing on?
1.
1,
2.
Oh, sorry, go ahead.
Oh, no, you're good. 1, well, so 1 to 4.
Uh-huh. In other words, every single place on this curve from there to there, it's rising.
Okay.
Every place.
Okay.
Okay? Now, in calculus terms, that means the first derivative is going to be positive. Have they even given you that term yet, first derivative?
Yeah, they have.
Okay. Well, there's a correlation between a function and its first derivative. And
Okay.
that correlation is that if the function is rising, increasing, its first derivative will always be positive. In fact, let me show you something else I have here that I generally try to show most all of my calculus students. Let me see if I can find it. And it is this curve right here. What you have here are 3 functions plotted one below the other. This top function is the function. This function is the first derivative of this function, and this one is the second derivative.
Okay.
Now, the beauty of putting these under one another is you can see that if we look at the first function, we're increasing from here to there, right?
Yep.
Well, notice what the first derivative is. The first derivative looks like it's decreasing, but that doesn't matter. It's positive. It's above the x-axis.
Okay.
Okay? The original function starts decreasing right there all the way to there. Notice the first derivative is negative in that whole area.
Yep.
Whenever the original function is decreasing, first derivative is negative. Then the original function turns around and starts increasing again. At this point right there, the first derivative becomes positive again.
Okay.
Okay? Second derivative is merely the first derivative of the first derivative. So I could do the same analysis. Let's look at this first derivative curve and the second derivative. Well, the first derivative curve is decreasing from there to there. That means the second derivative is negative from there to there, which it is.
Okay.
First derivative curve changes to increasing. Second derivative becomes positive.
Gotcha.
Okay? So this relationship is one of the most fundamental in all of calculus, is to know that if the original curve is increasing, its first derivative is positive. Because we know how to find first derivatives. So a lot of times if you have a complicated looking function and you can't tell where it's increasing or where it's decreasing, then you can tell by taking its first derivative.
Okay.
And determining where it's positive or negative. So number 3, these are pretty straightforward here. Tell me number 4, where is 4 increasing? What interval?
It's increasing on 3 to infinity.
And where is it decreasing?
Decreasing on negative infinity to 3.
Okay, good. 5.
Okay, so 5 is increasing from negative infinity to negative 4. And then again at negative 2 to infinity.
Okay, and what is it decreasing?
Decreasing from negative 4 to negative 2.
Okay, I think you got that. You understand,
Okay.
you understand that. Now,
Yep.
if I were to take whatever that function is and take the first derivative of it, I would find that the first derivative is positive from negative infinity to minus 4. And I would find that it was negative from minus 4 to minus 2, and I would find that it turns positive again from minus 2 to infinity.
Okay.
Okay? So I think we can probably dispense with through 8. I believe you've got that. And when you have corners or cusps, this is a corner right here. Okay? One of the things about corners or cusps is you cannot take the derivative at that point. There's no way I can figure out what the slope of the tangent to that is. It's not differentiable at a corner or a cusp, as opposed to 1 and 2, which are differentiable throughout the whole domain. 4, differentiable, but not at this point right here. 5, differentiable throughout. 6, differentiable throughout. 7, differentiable every place but right there at minus 2 on the x-axis. And 8, not differentiable right there at x equals 0. But is differentiable at those. Those are not corners. Those are round places. In other words, I know that if I figure out the slope of the tangent line, it's going to be 0 there, and it's going to be 0 there. Also, if I look at some of these other curves, it's going to be 0 there. It's going to be 0 there. It's going to be 0 here. It's going to be 0 there. In other words, when I talk about the slope of the tangent line, well, if I look right there, the slope of the tangent line is like that. It's not 0.
Right.
If I look at the tangent line right there, it's not 0. But when I get to that top point, it is 0, flat as a pancake. And then I go to this side, the slope of the tangent line is negative. In other words, as the function is decreasing, the slope turns negative. It goes from positive slope, meaning it was increasing, to negative slope. Down here again, I get another 0 slope, and then it turns positive again. So that's why this relationship between increasing and first derivative being positive is such, is because first derivative is the slope of that curve.
Okay.
If I bring up every point on this first derivative curve would be the slope at the equivalent point there.
Okay.
In other words, if that slope right there is plus 5, then I'm at plus 5 right there on the y-axis. That slope right there is 0. I'm at 0 on the y-axis right there. All right, let's have a look at some of these others. The only ones I can really read are 1 through 8. What else do you need to look at?
Do you want me to send another picture?
Well, some of these others look like they can be verbalized. I can't see 9 or 10. Do you need to worry about 9 through 16?
Let's see. Yeah, because at 13 it starts something else where they want like critical numbers.
Hold on.
And that's something I need help with.
Hold on a moment. And on the front of your book, who are the authors of your book? It's possible I have the same book.
I have Greenwell, Ritchie, and Lyle.
Okay, I don't have that book. Mine is Larson, Hostetler, and Edwards. And then I have another calculus book that is, hold on, Finney, DeMana, Waits, and Kennedy. So I don't have your book, which is a little unfortunate. Otherwise, I could just turn to page 5 in my book. But yeah, go ahead and take a picture of questions 9 through 16. Okay. Send that. And then see problems like 17 through 35. You could actually verbalize those relatively easy. That's just stating what the function is. So I wouldn't really need a picture of those kind of problems. But
I think we took 2 pictures. That might be common, David. So, but you can verbalize them if you don't need them. But I think there's 2 pages coming.
Okay, sounds good. It didn't take long before to get them. So I should have them here in a second.
Yeah, I told you, you'll work out a procedure that you and David will be comfortable with, and it'll work quite, really nice. After 1 or 2 visits with Patrick, we never had any problem. It worked out real nice. So those should be coming in, hopefully.
Okay. There we go.
If you need them, just give me a text.
All right, let me put both of them on there as long as I'm doing it. Okay, so what 9 through 12 is saying is if 1 through 8 were a derivative function instead of the normal function. In other words, you have your function, your first derivative, and your second derivative, and your third derivative ad infinitum. So sometimes the only information we have is the first derivative function.
Okay.
And it's useful to be able to figure out things about the original function if you know the first derivative function. Let's go back to this page here. Let's assume the only thing we knew was this. We couldn't see this.
Okay.
Well, we could still figure out a lot about this. We could figure out that it was increasing from there to there, because the first derivative function is positive.
Right.
We could figure out it's decreasing from here to here, and we could figure out it's increasing from here to here. Just based on that information alone, we could almost reconstruct the shape of that thing. So that's what they're asking you to do in these next problems. Is number 9 says, okay, look at function 1 and pretend that that is f prime of x, not f of x, and then say where it's increasing or decreasing. You understand what they're asking for?
Yep.
Okay, so on number 1, assuming that's f prime of x instead of f of x, where is f of x decreasing or increasing?
It'd be increasing from, let's see, so it'd be negative infinity to negative 1?
Yes. Where else?
And then it would be 3 to infinity.
Okay, where is it decreasing?
Then it's decreasing from negative 1 to 3.
Okay, good. Let's see, what's the next one they're asking about? Number 2. Let's do the same thing for 2.
Okay, so on 2, it's, let's see. So it's decreasing from negative infinity to 3.
Okay.
And at 5 infinity.
Okay.
And then increasing from 3 to 5.
Good. And number 7.
Okay, 7. So it would be increasing from negative infinity to 5, 6, 7. Is that 8?
Yeah, that's negative 8 right there.
Okay. And then also increasing at...
Let's go from left to right.
Okay.
Rather than, you know what I'm saying?
Yep, so then it start decreasing at negative 8 to negative 6.
Okay.
And then increasing it at negative 6 to negative 2.
Looks like negative 2.5 maybe.
Negative 2.5, okay. And then, let's see, decreasing negative 2.5 to negative 1.5.
Okay.
And then increasing again at negative 1.5 to infinity.
Good. And number 8.
Okay, so number 8 would be increasing from negative infinity to negative 3. And then, is it increasing again at negative 3 to 0?
Yes.
Okay.
And
then, I guess is it still increasing at 0 to 3? And then 3 to infinity?
Okay, so what might that look like? Let's draw that.
Okay.
That pattern you just described was increasing always, with a couple of places where it's 0. Curve like that.
Okay.
In other words, if it's increasing until that point right there where it flattens out, right here. It's a flat tangent line.
Okay.
Then it increases again, still increasing because it's still positive. By the time we get to 3, we're down to a 0 slope again, but that shows up right there. And it increases again. So I could actually say that this thing is increasing from negative infinity to infinity. I don't believe you have to account for these places where it's 0.
Okay, makes sense.
Yeah, I would think that the answer for this one is negative infinity to infinity, not negative infinity to minus 3 and then increasing minus 3 to that and so forth.
Okay.
Not 100% sure, but I'm almost 100% sure on that. All right, let's look at 13. All right. Do you know how to take first derivative?
Yeah.
Okay, good. Because this was going to be a hard problem to do if you didn't. If our f of x, we'll call it, rather than y, because f of x actually has some value in addition to just calling it y. And one of those values is you can say f prime of x. So let's figure f prime of x out. They've taught you the power rule?
Yeah.
Okay. Did they force you to go through the limit quotient definition of first derivative?
I don't believe so, but I'm not 100% sure.
Limit quotient definition is this one. Taking the limit of that as h goes to 0.
Okay.
That is the official definition of first derivative.
Okay.
Okay? That's the hard way to do it. But most every calculus course starts you out with forcing you to learn the hard way. I don't actually agree with that teaching technique. I think you're much better off starting on the easy slopes and working your way up to the expert slopes.
Right, I agree.
So let's just use the easy way, which is the power rule. So how do I find the derivative of this? What's the... and when you're taking the derivative of the sum, in other words, if you have a polynomial that has 3 terms in it, you can take the derivative of each term. In other words, the sum of the derivatives is the same as the derivative of the sums.
Okay.
Okay? And that's true with integration or differentiation. But when you talk about things being multiplied together, it's not true. In other words, if I try to take the derivative of this, much harder prospect. You've got to use the chain rule and all kinds of stuff. But for a simple polynomial, you can just use the power rule. So what's the derivative of 2.3?
It's 0, isn't it?
It's the derivative of 3.4x.
It's 3.4.
And the last term?
That one is 2.4x.
Minus 2.4x. Okay. So now I have f prime of x is equal, let's put it in proper ordering. And they want to know, well, what are the critical numbers? The critical numbers is where that thing is either undefined or equal to 0.
Okay.
So one of the most common steps in calculus is to take the first derivative and set it equal to 0. Because that tells us where all of these points are. In other words, that gives us that point, it gives us that point, doesn't give us that point, but over here it gives us this point and this point.
Okay.
Okay? So it's very common to take the first derivative and set it equal to 0. So if I do that, that gives me, for starters, my critical point. So x is going to be 2/3, I believe. 2.4, no, 2.4 divided by 3.4 is not 2/3. Whoops. Yeah. What is that? 12/17?
Yeah.
So that's my critical point.
Okay.
And the open intervals where the function is increasing, well, that's where this first derivative is positive. Is it positive to the left of my critical point or to the right?
Let's see. The first derivative?
Yeah. Yeah.
Let's see. Positive to the right?
It's to the left.
To the left? Okay.
In other words, when x is precisely 12/17, this thing is 0. That's how I got 12/17.
Okay.
And I can see that as x goes to the right of that, that becomes a bigger negative number than 3.4. So when I go to the right of 12/17, the first derivative becomes negative.
Okay.
When I go to the left of it, this is a linear equation we have here. In other words, this equation that I just came up with is something that looks like that.
Okay.
And that point is the y-intercept. That's 3.4. The slope is negative 12/17. But you can see that if I were to graph the curve, like I just did, and by graphing the curve I mean graphing that curve, the first derivative curve,
Okay.
it's a straight line. And this point right here is 12/17. The critical point being where f prime of x is equal to 0.
Okay.
Okay? And I can see by looking at this that everywhere to the left of 12/17, first derivative is positive, original function is increasing.
Okay.
Everywhere to the right of 12/17, I can see first derivative is negative, original function must be decreasing.
Okay.
And I think that answers everything for that.
Okay.
So let's look at 14. Function, this time I'll use y. Y is the same as f of x. The advantage of f of x is it tells you it's a function of x. When I say y, it could be a function of z, it could be a function of r, it could be any variable that you want over there. But the moment I say f of x, it can only be x's over there. And likewise, y prime means the same thing as f prime of x. So what's y prime here?
That one's going to be, well, if we put it in order, it'll be negative 0.6x minus 0.3.
Okay. What's the next step to find critical numbers?
Set it to 0.
Okay. So 0 equals that. Solve that for x.
So is it negative 1/2?
Huh? So now one way to look at this is well, again, I know that at x equal negative, I'm looking at a linear function there, right? So I know it's a straight line.
Okay.
And I know the x-intercept comes at minus 1/2. Because what I did was I set that equal to 0, so that means that's where it crosses the x-axis. That's where y is equal to 0, or y prime in this case. In other words, this axis here is actually y prime, and this is still x. Okay?
Okay.
Well, I can see the slope is negative 0.6, something that looks like that. Apologize for not being able to draw a straight line, but and if we look, remember we're looking at y prime here.
Yeah.
So the only thing we need is what's happening to the left of minus 1/2. Is the derivative positive or negative?
Positive.
Which means the original function is
Increasing.
okay. And the original function is decreasing where?
After the negative 1/2.
So x greater than negative 1/2.
Okay.
Yeah, in other words, your answers are going to be, to this problem, are going to be x equal minus 1/2 is the critical number.
Okay.
And B would be from negative infinity to minus 1/2. In other words, you always label these as the x coordinates. The function is increasing, and the function is decreasing for C minus 1/2 to positive infinity.
Okay.
And with linear functions, it's just going to be one critical point. Okay? If you end up with a quadratic after you take the first derivative? Well, that means your quadratic either looks like that or it looks like that. So it's going to have an interval where it's increasing and another one where it's decreasing.
Okay.
I guess the same as a linear, but you can get, in fact, 15. Let's look at 15 because our first derivative is going to give us a quadratic. So what is f prime of x here?
On 15, it would be, let's see, so,
best way to use that power rule is to start with that exponent.
okay,
3 times that times x squared. In other words, 3 times 2/3 and just take away 1 from the exponent there. So that's, and then the 3's cancel. So you end up with 2x squared.
Okay.
What's the next term?
2x squared, and then the next term is going to be negative 2x.
Okay. Minus 24.
Yep.
Okay. Now, we're going to set that equal to 0.
Okay.
And we need to solve this quadratic. The first step.
Take the 2 out of all of them?
Yeah. Let's just divide everything by 2. Makes it easier to factor. And I'll factor that.
Let's see. So would it be negative 4 and 3?
Good. Now, that means that we have 2 critical points.
Okay.
What are they?
The critical points are negative 3 and 4.
Okay, positive 4, negative 3. Now, this is a little tricky. We need to know, in order to know where this thing is increasing, we want to know where that is true, correct?
Yeah.
Okay. To solve this inequality, you need a line chart
Okay.
with your critical points on it. You don't need 0 on there. In fact, it might be more helpful not to put 0 on there.
Okay.
Okay. Are you familiar with these line charts on how to do this?
Kinda. Not like 100%.
Okay.
though.
The only thing we need to do is to test a point to the left of minus 3, test the point in between minus 3 and 4, and test the point to the right of 4.
Okay.
Well, pick a number to the left of minus 3.
Minus 5.
Okay. What's this? And then the only thing you really have to know is what the sign of each of these linear functions are. So minus 5, this would be negative. Minus 5, that would be negative. Negative times negative is positive. That means everywhere to the left of minus 3 is going to be positive.
Okay.
Pick a point in between.
1.
This is negative. That's positive. Negative times positive is negative. Every point in there is negative.
Okay.
Pick a point to the right of 4.
6.
This is positive. That's positive. Positive, positive. This is positive. That's how you do a line chart. Now, we know that this function is increasing from negative infinity to minus 3, decreasing from 3 to 4, and it's increasing again from 4 to infinity. So something like this, where if this is minus 3 and this is 4, it's increasing, 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 decreasing, 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 increasing, increasing, increasing. So the original function might look something like that. You'll recognize that that's what cubic functions look like. They have two loops in them. In fact, these are called extrema, local extrema. And what a local extrema means is that if I have a local maximum, it means that their points to the left and to the right are less than this point is right there. That's all local extrema means. Here I have a local minimum. Why? Because I have points to the left and to the right that are both higher than that point. Now, it's not correct to say that that is an absolute maximum because clearly the function is higher up there. Right. But in this vicinity, that is a local maximum. And in this vicinity, that is a local minimum. And the other thing we know is that the derivatives are 0 at both of these points. So if I gave you the original function and I said, well, where are the derivatives equal to 0? You take the first derivative, set it equal to 0, and find out what those 2 points are. Okay. And you don't know whether those are minimums or maximums, but you know that there are a local extrema there. Okay. And there's another test to determine whether it's a minimum or a maximum. And that's called a first derivative test, and it's also called a second derivative test. Have you dealt with second derivatives at all? Yes. Okay. There's nothing magical about second derivatives. It's just the derivative of the first derivative. Right. So let's take the derivative of this one here. So on 16, what is f prime of x?
So that one's going to be on 16, you said? Okay, so it'll be 2x squared minus 2x minus 4.
Again, we're going to set it equal to 0, take out the 2, and we're going to have x squared minus x minus 2 equals 0. Factor that.
Let's see. So it would be negative 2 and 1.
So again, we're going to do our line chart test because in order to answer parts B and C, we need to know where the second derivative is positive and where it's negative, the first derivative, excuse me. So I need to answer this question, and I need to answer the question when I turn the inequality sign around. And you answer that by these line charts. Okay. I didn't need a line chart when my first derivative was linear. Right. Because it was really easy to tell. You're on one side of the 0 point or the other. But when your first derivative is greater than linear, you need these line charts to answer these questions. Okay. So the critical points are
2 and negative 1.
Okay. And tell me what's going on everywhere around those points.
Okay, so
what's happening to the left of negative 1?
To the left of negative 1, it's going to be positive.
Okay. What's happening in between them?
And then in between them, let's see.
0 is a real good number to use if it's in between your two numbers.
Okay. So then it would be negative in between.
Okay. And to the right of 2?
To the right, it'll be positive.
Okay. So to answer the question, what intervals is the function increasing on?
It's increasing negative infinity to negative 1.
And,
and 2 to infinity.
okay, and it's decreasing.
-1 and 2 to 2.
Cool. All right, let's see. Let me go to the next page here. Just as long as I got this up, let me give you some calculus you may or may not have had yet. If you had inflection points or concavity?
No.
These are kind of important concepts. Let me just briefly explain them to you. Even if you haven't had them yet, you'll get them shortly. Notice how this curve, the original function, curves that way? That's concave down.
Okay.
Notice how it curves up? That's concave up.
Okay.
This derivative is only concave up. This has no concavity at all to it.
Okay.
The point in between where the concavity changes from up to down is called the inflection point. It's right where my little hand is there. I don't know if you can see that or not.
Yep, I can.
In other words, there has to be some point in between here and here where that concavity is no longer concave down and it switches to concave up. That's the inflection point. Notice that the second derivative is 0 at that inflection point.
Okay.
Also, wherever the original function is concave down, the second derivative is negative. When the original function is concave up, the second derivative is positive.
Okay.
So that's another real key relationship between functions, first derivatives, and second derivatives, is this concavity principle. And that's all I'll say about it for now. Let's see. Let me open this one right here. Okay. The only thing I don't have on this are the instructions. I assume it's the same.
Yep, it is.
Okay. Well, you know how to do the cubics. Because, first of all, whenever you take a derivative of a polynomial, you reduce its degree by 1. So if I start with a cubic, after I take a derivative, I'm going to have a quadratic.
Okay.
This one is a quartic. So after I find the derivative of this, I'm going to have a cubic. Well, let's look at that, because I know you know how to do the 17 and 18. You agree?
Yep.
Okay. So let's look at 19. First of all, 19, what is f prime?
That is going to be 4x to the third plus 12x to the second. And let's see, plus 8x.
Okay. Now, this is a cubic, but it's a cubic that I can factor. So let's do some factoring of this. In other words, we're still going to use our intention to set that equal to 0.
Okay.
But let's factor some stuff out first.
Okay.
What's the greatest common factor?
4x.
What do we have left over?
You have x squared plus 3x plus 2.
Well, now I can divide both sides by 4x. Well, no, I don't want to do that yet.
Okay.
Let's factor this quadratic further.
Okay. Let's see. So is it 2 and 1?
Huh? Your hesitation suggests that we need to spend 15 or 20 minutes on factoring. I think I can straighten you right out.
Okay, perfect.
But maybe not today. We'll
we can have another day.
But factoring is something you never have to know how to do.
Okay.
Okay, so I'm going to set this equal to 0. What are my critical points?
They are -2 and -1.
One more.
And 0.
Yes.
Okay.
And that's an important one. And that's why I couldn't divide both sides by 4x.
Okay.
If you ever divide by a variable that can be 0, and 0 is one of the solutions, you'll lose it. You
Okay.
won't see it anymore. Notice that if I had divided both sides by 4x, I would only have these two critical points.
Right.
Well, 0 is an important one. So what's going on to the left of -2?
To the left of -2, let's see.
That's all we need to do to answer that. You don't want to actually come up with the numbers. It's just wasted mental arithmetic.
Okay.
Just do the signs. In other words, let's say you pick -3. So that's clearly a negative there. What's this?
That's a negative as well.
What's this?
That's a negative.
So
too.
all three negatives multiplied together.
It's a negative. Okay.
Now let's try -1.5.
Okay. So that's going to be a negative. Yep. And then that's a positive. And that's a negative.
So the net?
Is positive.
Okay. Now these usually alternate. I've actually heard some teachers say that you can just, once you get the pattern, you know the rest of it. But
Gotcha.
I'm not positive of that, to be honest.
Okay.
I'm sure that there are some functions that go negative, negative, positive, negative, negative, and so forth.
Right.
So let's test all of them. What's going on at -0.5?
-0.5, so the 4 would still be negative, and then positive, positive. So negative?
And to the right of 0?
Positive.
Okay. So the original function is increasing on what interval?
It's increasing on -2, -1, and then 0, infinity.
And decreasing?
Decreasing -infinity to -2, and then -1 to 0.
Okay. And that's the way we're going to solve all of these problems.
Okay.
Now, this was only very doable because there was no constant. I'm sure, well, I don't know if you remember or not, but if you take a cubic that has a constant, finding its zeros is no easy task.
Right.
In fact, it can be like a 20-minute problem.
Okay.
Okay. If you can't factor it easily, then it's not easy to get it to that state. You know, if I had a number like 3 to that, well, you'd probably have to use a calculator to find the zeros. But whatever they are going to be your critical points. And that's all you'd have to do. In other words, if you end up with a first derivative being a cubic that you can't find the zeros on easily, you can use a calculator to find the zeros, you can use grouping if it fits grouping, or you can go so far as to using the rational factor theorem, and that's the 20-minute solution.
Okay, gotcha.
This one we didn't have to worry about it because they didn't give us a constant, which means we were able to factor out the x, leaving a quadratic, and getting it. In other words, we were able to get it into 3 linear factors. That's the key on all of these. Once you get it into 3 linear factors, then you can apply this line chart. Now, this line chart technique, even though I don't know that we're going to see any problems that are like that, we might, I'll take a quick look here, but it's more useful when you have something like this, a quotient.
Okay.
If I say x plus 3 over x minus 1 has to be greater than 0, what are the critical points? Whatever makes the denominator 0 or the numerator.
Okay, so 1 and negative 3.
And then I do my line chart. I put 1, I put negative 3. I do exactly the same thing. If I'm at negative 4, I get negative divided by negative, which is positive. If I'm at 0, I get negative. If I'm at 2, I get positive over positive. In other words, you can use these line charts whether you have a product of two linear factors or a quotient of two linear factors.
Okay.
And it's actually, when you have a quotient, it's much harder to come up with the answer without using a line chart. I'm not sure I'd know how to do it. With the product, I could probably figure out how to do it. But when you have a quotient, the line chart is necessary for sure.
Okay.
Take a look at some of these. We only have a few minutes left. Let me see if there's any on here that are going to present you with problems.
Okay.
Notice these quartics do not have an x. That means when you take the derivative of it, you're not going to have a constant. And you're going to be able to factor out the x, and you're going to take it down to 3 linear factors. Just like 19 we did. Okay?
Right.
20 is going to be the same thing. 21. How would you do 21?
That's a good question. So that one I don't know how to do.
Well, what's y prime?
Negative 3.
The original function, is it increasing or decreasing?
It is decreasing.
Everywhere.
Okay.
Because y prime is always negative.
Okay.
In other words, this is y prime. There's negative 3 right there. Well, the original function, you'll notice, is a linear function with negative slope. That's always decreasing.
Gotcha.
So that's why the first derivative is always negative.
Okay.
And we've got a couple minutes. Let's do this one because that's going to require the quotient rule.
Okay.
Now this is an interesting one that you have on this page because this tells me that you've probably had the product rule, the power rule, the quotient rule, and the chain rule.
Yep.
We're going to need the chain rule for 25.
Okay.
Okay. But we only have time for one. Let's do 23. What is f prime of x?
Okay. So the quotient rule.
Now, do you have a handy way of memorizing the quotient rule?
I don't.
I'll give you a great one.
Okay.
Starts with the bottom, ends with the bottom squared.
Okay.
Okay. Now, you know the top is the bottom times the derivative of the top. We'll note that like that.
Okay.
Subtraction is going on, not addition. So, in other words, the product rule, addition is going on. So I can put these things in either order. But with the quotient rule, I've got to put the thing on the left, it's got to be the bottom times the derivative of the top. Minus, well, this has to be the reverse of that, right? So this would have to be the top times the derivative of the bottom all over the bottom squared. So if you remember that it starts with the bottom, then you can't mess that up. In other words, it'll never be the bottom derivative times the top. It'll always be the bottom is the first thing you're going to write. Times the derivative of the top minus its reverse all over bottom squared.
Okay.
And I do think that's the easiest way to memorize it, because you really
Yeah.
can't really mess it up. So in these two functions, what's this part?
So the bottom would be x plus 1 times 1.
Okay, minus,
X plus 2 times 1 again. So
all over,
x plus 1 squared.
simplify.
It would be, let's see, would it be negative, okay,
In other words, the x's cancel,
okay,
and you got 1 minus 2.
gotcha.
So negative 1.
Okay.
So now we have to figure out where that thing is greater than or less than 0. Well, we're still going to use a line chart. What's the critical number?
The critical number is it negative 1?
That's the only critical number.
Okay.
Okay. So on my line chart, there's negative 1. What happens to the left of negative 1?
Let's see. Is it negative?
What happens to the right of negative 1?
Is it still negative?
Because the denominator is always positive. No matter what
Right,
x is, if I'm squaring it, I'm getting a positive number.
Okay.
So this thing is negative throughout its domain, which means the function is decreasing everywhere. Now, that's hyperbolic in nature. Well, how does a hyperbolic function decrease everywhere? How about if it looks like this?
Okay.
Can't ever be negative 1, but it's still decreasing throughout the domain.
Okay.
Well, actually, the interval, this is important. The interval is actually negative infinity to 0, and in this case, definitely 0 to positive infinity. In other words, you could not say that it's increasing from negative infinity to positive infinity, because we have this vertical asymptote right there. So it doesn't increase across that asymptote or decrease across that asymptote. It just increases up to it. Okay? Different than the straight line. That decreases everywhere. But in this hyperbolic thing, it's two different intervals.
Okay.
Okay, Molly, why don't we end it there?
Okay.
And I'll just let your dad take care of making future appointments unless you find a time and a day that you really like and you want to lock it up, then just have him call me or you call me or whatever, and I can do that from my end. He can't do it from his end.
Okay, gotcha.
Okay?
Perfect.
Right.
Thank you so much.
Nice meeting you, and good luck.
Okay, thanks. Have a good day.
You too. Bye-bye.
Bye.